Welcome to another Mathologer video. Today we'll take a well-earned break from all the heavy-duty algebra of the last couple of videos. Today it's all going to be super visual and super accessible. Promise. Okay, to start with, let me first get you hooked. 3 colors: red, yellow, blue. Put down a row of 10 hexagons and color them randomly. There, that's one possible coloring. Draw a row of 9 hexagons underneath. The color of one of these new hexagons depends on the colors of the 2 hexagons above it. See whether you can guess what the rule is. Yellow and red add to blue. Red and yellow add to, also blue. Yellow and blue add to red. Easy, right? I'm sure you've guessed already that whenever we are adding 2 different colors, the result is the 3rd color, and so on. Blue plus yellow is red, yellow plus red is blue. Okay, what if we have to add a color to itself? Well, red plus red is red. That's the most natural rule. Agreed? Agreed. Draw a row of 8 hexagons underneath what we've got so far. And using the same rules, just keep filling in colors and drawing rows until it all ends, like this. So you end up with an equilateral triangle composed of hexagons. Important observation: once the colors of the top row have been chosen, all the other colors are pinned down. Here are a couple of examples of triangles resulting from different choices of colors in the first row. There, and that one, and that one, and that one, and that one. Very pretty. Before we take a closer look, let's play a speed game. In a moment, I'll randomly color this first row. Then I'll count down from 5 and ask you to decide what the resulting color of the bottom hexagon is. Get it right and you win a lifetime subscription of Mathologer videos. Yes, okay, it's free anyway, but you win bragging rights. What are you going to do? Of course, you can just guess for a 1 in 3 chance. On the other hand, since the first row will determine all the colors of the hexagons below, you can just calculate the color of the bottom hexagon. If you're really quick, or if you pause the video. Anyway, time to go. Ready? Well, ready or not, here we go. Okay, make your guess. What's the color of the bottom hexagon? 5, 4, 3, 2, 1. And the answer is yellow. Did you get it? Without pausing the video or just guessing? Sounds impossible? Well, it turns out that there is a super surprising shortcut for this calculation. It turns out that the color of the bottom corner of our triangle is simply the sum of the 2 colors in the top corners. There, yellow plus yellow at the top is yellow at the bottom. Yellow plus blue at the top is equal to red at the bottom. Blue plus red is yellow. Blue plus blue gives blue. It really works. Pretty amazing, isn't it? Choosing different colors in the top row gives very different colors of our triangle. And yet, the colors of the top 2 corners alone determine the color of the bottom corner. Weird, huh? Well, it gets weirder. What if instead of 10 hexagons at the top, we started with 9 hexagons? Well, then the shortcut doesn't work anymore. For example, stripping a slanty column off of the width 10 triangle over there gives us a width 9 triangle. And here the shortcut clearly doesn't work. Blue plus blue should be blue, not yellow. Stripping off another row gives a width 8 triangle. Again, the shortcut doesn't work. Keep on going. In this case, blue plus blue is blue as expected. However, if instead we had stripped things like this, we get a width 7 triangle that doesn't work. Also, width 6 doesn't work, and neither does width 5. Okay, so why is 10 special? And are there any other special numbers? To hunt for clues, let's have a closer look at this larger triangle. Notice all the smaller solid colored triangles here and there. It's raining little triangles. Yeah, raining. Maybe this reminds you of something? Can you think of a famous mathematical supermodel dressed in little triangles? No? Okay. Have a look at this special supersymmetric example. In this case, the first row is entirely yellow, except for a single red hexagon in the middle. I first encountered a strange shortcut phenomenon in an article by mathematicians Erhard Behrends and Steve Humble in the Mathematical Intelligencer. It reminded me of the famous Sierpinski triangle fractal, in which it is also raining little triangles. Beautiful pattern, isn't it? And I was also reminded of the pattern on a giant snail shell that I bought a couple of years ago in a butcher shop here in Melbourne. Butcher shop? Yep, you can find the strangest things in Australian butcher shops. And of course, the whole summing two above gives the one below business should be very, very familiar. Yep, our good old friend Pascal's triangle is based on the same sort of growth principle. Steve Humble, one of the authors of the article I mentioned earlier, created the three-color game as a mathematical outreach activity in 2002 and discovered the shortcut while demonstrating it to kids. Today, I'd like you to imagine that you are a mathematician who, just like Steve, has stumbled across this mathematical gem. So, as a true mathematician, you are now cursed to not be able to sleep until you've come up with an explanation for the shortcut and how it relates to the snail pattern and to Pascal's triangle and Sierpinski's triangle. Well, let's find out together, shall we? In 5 easy chapters. Okay, time to investigate. Why does the shortcut work for widths 10 triangles? And are there any other special numbers? Well, we already saw that 9, 8, 7, 6 and 5 are not special. And that's where we stopped. I wonder why. Let's have a look at 4. Blue plus yellow is red. Probably also just a fluke, right? Wrong. If you keep experimenting with widths 4 triangles, you'll find that the shortcut always works. 4 is also special. Okay, let's say it's been a long night and we're all pretty brain-deaded. In this state, can we still show that 4 is special? Yes, no problem. There are 4 hexagons in the first row and 3 possible colors. This translates into 3 to the power of 4, that's 81 different ways to color the first row. This means that there are exactly 81 widths 4 triangles. And even if I'm half dead, I can quickly throw together a computer program that will in an instant list all these triangles and check that our shortcut works for all of them. Actually, if we're not quite so brain-deaded, then we can use symmetry in permuting colors to reduce the number of triangles we need to check. So a little challenge for you: how many essentially different widths 4 triangles are there? Let us know in the comments. Of course, checking all those triangles doesn't tell us why 4 is special. We still haven't proved that 10 is special and we haven't checked many other widths. So it's time to go deeper. With my computer program, I can also quickly make up larger width triangles and check that among all the numbers from 1 to 100, the only numbers that appear to be special are 2, 4, 10, 28 and 82. 2, 4, 10, 28, 82. Tricky! Nope, not tricky at all. Did you spot the pattern? These numbers are all 1 up from a power of 3. 4, that's 3 plus 1. 10, 3 squared plus 1. 28, 3 cubed plus 1. 82, 3 to the power 4 plus 1. And let's not forget 2 at the beginning. 2 is 3 to the power of 0 plus 1. The plot thickens. And based on what we've got so far, we conjecture that exactly the numbers 1 up from powers of 3 are special. Now, let me show you something absolutely beautiful. A proof that all these numbers are indeed special. This one is really good, promise. Let's begin where we began, by showing width 10 is special. So let's start with any old width 10 triangle. Now focus on these hexagons here. Then these three hexagons are the corners of this width 4 triangle. And since width 4 triangles are special, the top two corners must add to the corner at the bottom. The same is true here, and here, and here, and here, and here. And now, well, I probably don't even have to say it, right? Can you see what's happening? We just showed that over there, any two adjacent colors add to the color below. And what this means is that these highlighted hexagons combine into a width 4 triangle. And therefore, because 4 is special, the top two corners add to the bottom corner. But since the top corners of this width 4 triangles are also the top corners of the original width 10 triangle, it follows that the top two corners of a width 10 triangle add to the bottom corner. Always. In other words, 10 is special. Ta-da! An argument like this makes my day. So on the scale from 1 to 10, how beautiful an argument is this? Yep, we're doing polling now. Let me know in the comments what you think. To prove that 28 and indeed all the other powers of 3 plus 1 are special, we just repeat this argument over and over. Here just a quick animated first iteration of the argument that shows that 28 is special using the fact that 4 and 10 are special. So nice. And a little challenge for you. Can you think of a second way to argue? Hint, switch the roles played by 4 and 10. Anyway, I suspect that at this point most people would declare the mystery solved. Time for a cat video? Well, that's not what we do here on Mathologer, right? Is it really just a big coincidence that width 4 is special, or is there a deeper reason? Also, we know that 2, 4, 10, etc. are special, and we suspect there are no others. But how can we be certain? And what's up with all these similar phenomena? Sierpinski and the snail shells and whatnot. Are there any beautiful connections? Ready to go deeper? The basic rule of two adjacent colors in one row summing to give the color immediately underneath just cries out for us to have a look at the tip of Pascal's triangle. Right? Any two numbers in this famous number triangle add to the number right below. Here, 4 plus 6, that's 10. 5 plus 1, that's 6. Okay? This addition process is very similar to our coloring scheme, but there are also obvious differences. In Pascal's triangle, there are no hexagons. We're adding numbers instead of colors, and everything starts from the tip rather than from a row of numbers. Okay, you want hexagons? Well, here are a couple. What else? You want the whole thing to start from a row, not from the tip? Not a problem at all. So we can think of Pascal's triangle growing from an infinite row of zeros with a single one thrown in somewhere in the middle. And that should also remind you of the Sierpinski colored triangle we saw earlier, which starts from a row of yellows with one red exception in the middle. Interesting, huh? Anyway, to keep things uncluttered and to escape from this frame here, I'll hide all the zeros anyway, and we'll return to the familiar picture of Pascal's triangle. Okay, just remember that the zeros are still there, but hidden. Now, what about colors? Well, here the first idea that comes to mind is to color the hexagons according to one of the natural ways to split the integers into a finite number of classes. For example, coloring all the odd numbers dark and the even numbers white, we get this. That looks promising, and it's even more promising when we zoom out to reveal a larger slice of our triangle. Whoa, pretty impressive, huh? In fact, if you keep zooming out, our ever more detailed even-odd triangles will converge to the famous Sierpinski triangle fractal. Anyway, it's most definitely raining little triangles in there, just like in our three-color triangles. Another way to interpret our odd-even coloring is to say that we color according to what remainder a number has on division by 2. After division by 2, the possible remainders are 0 and 1. For odd numbers, the remainder is 1 and we color dark. For even numbers, the remainder is 0 and we color in white. What we then get is Pascal's triangle using what is called base 2 modular arithmetic. Fancy words, but it's just even and odd. So, wherever you see 1 and 0 next to each other, there will be a 1 underneath. 0 plus 1 equals 1. That translates to even plus odd equals odd. Similarly, 0 plus 0 equals 0. And then there's the slightly weird 1 plus 1 equals 0, which amounts to odd plus odd equals even. Okay, we found a natural numberish way of coloring with two different colors. What happens now if we play our game with the even-odd rule? Are widths 10 triangles still special? Here are a few random widths 10 triangles you get this way. There's one, there's another one, there's another one, there's another one, there's another one, and, well, is 10 still special? No, definitely not. If it were, black and white on top should give black at the bottom, right? 1 plus 0 equals 1, not 0 we got at the bottom. But don't despair. There are also special widths for our even-odd coloring. However, instead of 1 plus powers of 3, this time it's 1 plus, can you guess it? Powers of 2. It is easy to prove that all these numbers are special using the same collapsing argument as for our red, yellow, blue triangles. This lovely and simple construction also suggests a very natural model that can be used to at least partly explain the formation of snail shell patterns. A snail shell grows in thin layers that are added onto its lip. In our mathematical model, these layers are the horizontal rows of hexagons. Then the color of the hexagons in each new layer is determined by the simple rules for adding odd and even numbers. This is all very neat, and it is based upon a biological mechanism that can be observed where the characteristics of existing cells determine the characteristics of newly formed adjacent cells. So nature has already found a lovely application of the games we are playing here. Do any of you apply similar this plus that mathematics in anything you do in your working life? Let us know in the comments. Okay, so this is what Pascal's triangle looks like when you color it according to the remainder after division by 2. For our original game, we used 3 colors. So let's see what happens when we use remainder on division by 3. Of course, now the possible remainders are 0, 1, and 2. And let's respectively assign them the colors yellow, red, and blue. Then this is what you get. There, and ooh, very pretty again. Now compare this triangle to the nicely symmetric triangle that resulted from our original 3-color game. Yep, so close. Not quite the same, but we're definitely on to something. Okay, let's have a close look at the growth rules for our remainder 3 Pascal triangle. So with Pascal, to add a and b, we simply go a plus b mod 3. Now in terms of colors, this doesn't quite correspond to what happens in our original color game. For example, in our original color game, red plus red equals red, but Pascal gives the answer as blue. However, there's a super simple algebraic adjustment to get perfect agreement. Can you see what we need to do? Well, first notice that at least the middle rules always work. But to make things work completely, these 2's need to be replaced by 1's, and these 1's need to be replaced by 2's. And there's a really simple tweak to do that. Just go minus a plus b here. Let's check that this tweak really has the desired effect. Okay, minus 0, well, it's 0. Nothing changes here, which is great. What about the top rules? Well, now we have minus 2, but in mod 3 arithmetic, minus 2 is the same as minus 2 plus 3, which equals 1. Got it? And on the bottom row, we now get minus 1, which is equal to minus 1 plus 3 equals 2. This really works. So we've done it. This algebraic rule has captured the mathematical soul of our original 3-color game. As a first application of this clever insight, let me show you how you can see pretty much at a glance why 4 was special in the original game. Remember, originally we showed this by listing all possible 81 widths for triangles and checking that the shortcut works for all of them. We can do much better than that using just a little algebra. We start with 4 random colors, A, B, C, D, and then we can simply calculate the remaining colors like this. But of course, in mod 3 arithmetic, 3 times anything is just the same as 0. And so, fantastic. B and C just cancel out, and the number at the bottom only depends upon the numbers A and D in the top corners in the right way. So our simple calculation confirms once again that 4 is special for our original setup. But actually this calculation tells us something about Pascal's triangle as well. Instead of our original 3-color game, take a look at the Pascal 3-color game. Then the algebra is exactly the same, except all the minuses here turn into pluses. And again, the 3 times somethings in the bottom hexagon disappear. So for this Pascal 3-color game as well, the number 4 and therefore all those other numbers, 10, 28, etc. are special. What about the odd-even, black-white, mod 2 Pascal game? In the case of this game, we only need to worry about this smaller part of the triangle. Why? Because 2 times anything is even, and so it reduces to 0 mod 2. And so the 2b term in pink zaps to 0. This proves width 3 is special for the mod 2 game. And then, by our collapsing argument, we can see that all powers of 2 plus 1 are special. Of course, we can play the same games using any number of colors. With m colors, we can then use the sum modulo m, or its negative, as our generation rule. And then the same algebra and our contraction argument can pin down the corresponding special numbers. For this, we need to identify those entries here for which all the middle coefficients are multiples of m. As we've already seen, for m is equal to 2, the first time this happens is here. And as we've also already seen, for m is equal to 3, the first time this happens is here. And now a challenge for you, a tiny little challenge. Figure out the smallest non-trivial special numbers for m is equal to 4, 5, 6, etc. until you get sick of it, okay? A hint, just focusing on the blue entries, can you see another Pascal triangle? If you're keen to learn absolutely everything else there is to know about these games, check out the Intelligencer article by Erhard Behrends and Steve Humble that I mentioned earlier. In particular, in this article you can find a proof that the special numbers we've spotted are really the only special numbers. This proof is based on a 1909 article by the Indian mathematician Balak Ram in the Journal of the Indian Mathematical Club. How on earth did they find that one? So using the special numbers that result from our addition rules, we can fashion ourselves some nifty keys with which to explain those striking self-similar patterns. Let's have a closer look at the triangle over there. A reminder, we got this triangle using our original 3-color addition rules, starting from a row of yellows with a single red hexagon right in the middle. Okay, so the whole thing starts with this row of hexagons at the top. Since yellow plus yellow equals yellow, it's clear that we'll get those two huge yellow oceans on the left and right, right? Now, what about the mystery white region in the middle? Let's figure out what yellows we get there. In order to do that, I'll make myself one template each for the special numbers 4, 10, 28, and so on. I'll now place the template so that the two upper corners sit on yellows in the outer regions. Whenever this is done, we know that the bottom corner of the template must also be yellow. Let me show you. All makes sense, right? But just to pinpoint exactly where the self-similarity of the pattern comes from, think about the yellows being built in this order. When we place one of the templates so that its top two corners lie in the left and right oceans of the yellow, the template generates one of the centered yellow triangles, like this. This takes care of all these centered triangles. There, all of those. But now focus on this off-center region here. What's happening here? Well, we already have large lakes of yellow on the left and right, plus a starting row all yellows with one hexagon of a different color in the middle. So within this frame, we can now generate centered triangles exactly as before. There, and so on. This really gives a very good intuitive feel for where this self-similar pattern comes from, doesn't it? And it's not that hard to turn this intuition into rigorous proofs for the fractal nature of these patterns. There's one very surprising feature of the original 3-color game that I did not mention yet. When you rotate one of the triangles colored like this, you get another triangle of the same type. So what this means is that this new triangle also grows from its first row. This feature is shared by all the other negative mod M colorings, but not by the straight Pascal mod M colorings, except mod 2. Can you think of the simple explanation for this phenomenon? Anyway, to finish off, let me just show you an animated introduction to the most natural, three-dimensional counterpart of Steve's 3-color game that also shares the 3D counterpart of the rotation feature. And that's all for today.